All right, so here we go. Last part of chapter 11. We enter into the business or information about the hydrates. Now, if you play sports and your coach tells you to hydrate, what are they telling you to do?
Water.
Drink water, all right? This is just chemistry version of, hey, compounds absorb water and they become hydrated with H2O water. So what happens is we have our chemical compound, we have this water be absorbed by that chemical compound, and as a result, it has water surrounding that compound, okay? Now, the reason that we have to talk about this is one, it relates to moles. Two, 3/4 of Earth's surface is composed of water in some form. A lot of compounds are going to be dissolved in water. A lot are going to be hydrate compounds. Okay, we're going to talk about naming and writing the formula. Pretty simple process, and then we're also going to talk about how we can develop that formula for our substance. Okay, questions? Does anybody need this? All right. So why hydrates are important, okay? If we have anhydrous substances, which if you're in the agriculture community right now with all the fields being plowed, they're putting in anhydrous ammonia, okay? What that does, they put it in the fields, it absorbs the water in that field, and it basically revitalizes that soil, prepares it for next year's planting season. Okay. We also can use things such as desiccators. In a simple desiccator example, has anybody gotten like a new pair of shoes or a package and it has that little packet that says "Do not eat"?
Yeah.
That is something that will be an anhydrous compound and absorbs any moisture that's in that box in the shoes itself. Those things actually kind of cool. You can throw them in the oven and it will take the water, evaporate the water out, and you can reuse them. Most people just throw them out. Okay. Questions over this? Also, down here, the solar energy part. Water can absorb a lot of energy, and we can use that energy for useful things. Now, think about a pool. For those that have a pool, water initially is really cold. Over the summer, it heats up, and it will maintain that heat even with some cool mornings because it absorbs a lot of that solar energy. Okay. Questions? Anybody need it? Good. All right, so we start out with naming and writing the formula of our particular compounds. Number one, I know we got to reach back to chapter 8 with ionic compounds, but number one, we name that ionic compound the same as we would previously, okay? And I'm not going to get crazy outrageous on the naming of those compounds. It's going to be pretty obvious what that compound is. What I want you to focus on is the amount or number of waters, okay? So it's going to be a hydrate compound because you're going to see a dot, some number, and then H2O to represent water. That number next to the dot represents how many waters are attached to each formula unit or each of those compounds, okay? What we use to represent the number is the prefix sheet for our values there. So again, 1 would be represented by mono, 2 represented by di, 3 tri, so on. I'm going to give you that sheet. And then to indicate that you are dealing with water, all you do is you tack on that hydrate word at the very end, right? So we'll go over some examples of naming and writing the formula here in just a few moments. But any questions on this? All right, does anybody still need this? All right, so let's try some examples out here. Okay, so we're gonna go from formula to name on part A, and then on part B here, we'll go from name to our actual formula. Okay, so CaCl2. I'm going to go pretty quickly over this, but remember, you can look up these on your ion formula sheet. And so if we look up CaCl2, we would have Ca would simply just be our particular calcium. And if we look up Cl, it's not chlorine, but what does the ending have to change on our compounds here? What is that? Heard it? Chloride. Yep. So calcium chloride. Check. That's what we've done previously. Okay. Now we have DOC, which represents that water is attached to this calcium chloride, and we have two of them. What's the prefix that is associated with 2? Di. So we would give a little space here, we put di, and right next to that prefix di, we would put hydrate for that water. And that's all we would do. We're just writing the name exactly how we see it. The only exception is we add the prefix and hydrate for water. All right? Questions? All right, copper 2 sulfate pentahydrate. With this formula, I'm going to start out with copper 2 sulfate. Now, I'm going to backtrack a little bit here. Remember, the charges have to be indicated, and copper's charge is indicated by that Roman numeral 2. So we get copper 2 plus. Sulfate. If you looked up sulfate on your chart, it would be SO4 with a 2 minus. Now, if we swoop and loop here, and we have our 2 and 2 charges, what happens with both of those 2's? Cancel out, and so our formula for copper 2 sulfate would simply be CuSO4. Now, the pentahydrate, in this particular scenario, we have to say, all right, we're going to draw our dot because that's going to tell us water is connected. And I look back here at this. Penta is the prefix for what? 5. And then hydrate just represents that. That is water, so we put that as H2O. And so that would be our formula for copper 2 sulfate pentahydrate. Any questions? Anybody still need this? All right, so now let's get down to our math business here, and let's go through this. So it seems like a lot of steps, but it's a lot of real life applications. Okay, so we're going to have a hydrated compound. Now, to get rid of water, what do you think we have to do to that water? What would you do if I said make a pot of spaghetti? You would heat it up by you would essentially boil or evaporate that water. Okay, so what happens? We heat it up really, really hot. That water is going to evaporate. So now water is in the atmosphere as a gas. It's away. It's gone. And at the end of the heating, we're just left with that particular anhydrous compound. So the compound without water. We're going to have 2 values. 1, mass of water. 2, mass of that anhydrous compound. Mass in grams is great, but we really need this in moles. All right, so we're going to convert both of those things to moles, and then we can do a ratio. And our ratio to determine our formula is always going to be the number of moles of water on top divided by your moles of your anhydrous compound, right? At the end of the day, that ratio is going to give us a relatively whole number, and that whole number is going to be used right in front of that H2O. and that's going to be able to help us determine that particular formula. Okay. This, I know it seems like a lot of steps, but it's much shorter types of problems than our empirical and molecular formulas, just because we can essentially get to where we need to be in a lot quicker path. All right, any questions? Does anybody still need this? Okay, gotcha. All right, so let's try this example here. Now, highlighted in yellow, I realize you don't have that, but those are our molar masses. They'll kind of help speed this problem along here, okay? We have a mass of 2.5 grams of blue hydrated copper 2 sulfate. In this scenario, we want to find out what X is, how many waters we have. We already have the formula. We have X there. And then we heat this hydrated compound off to evaporate the water. At the end of heating, we're left with only 1.59 grams of that copper 2 sulfate. We want to know what the formula is, the hydrate, and then at the end of the day, we want to name this. So what we first need to do is this. We want the mass of our water, or of H2O. So what we have to do is this. We need to take our original mass of 2.5 grams, and that's everything. Water plus our anhydrate compound, and we need to subtract it from what remains. So we're going to take 2.5 and we're going to say minus 1.59 grams. Okay? So if we take 2.5 grams minus 1.59, what do we get? Should be 0.91 grams of water, okay? Now, we got the mass of water, and I said before when we were writing the steps down, we also need to think about the mass of our anhydrous compound, which I'm going to circle this 1.59 number again, because that 1.59 number is our mass of our anhydrous compound, which in this case is copper 2 sulfate. Then, like I said, grams is nice because we can measure it, we can throw it on the scale, but we have to convert it to something useful, something that allows us to compare, which is mole. Yes, very good. So we start out, I'm going to do this one at a time. We say our, up top here, our grams of H2O, we say times, and I'll ask you this. What unit has to be down and diagonal?
Grams.
Very good. Grams of H2O. On top, we can go to moles of H2O. And here for H2O, we have a molar mass of 18.02 grams per mole. This 18 number, in this case, does it go on top or on bottom? It goes on bottom with G for grams. So we put 18.02 grams to our 1 mole. And I do this. Remember, diagonal numbers divide. So 0.91 divided by 18.02. And we end up, I'm going to go 4 decimals here, 0.0505 moles H2O. Okay, that's great, fine and dandy that we have that here. We got to get moles of our copper 2 sulfate. So we say times, draw our line, what unit cancels down the diagonal? Grams of that Cu SO4. We go to moles of SO4, or excuse me, moles of Cu SO4. And the molar mass of copper 2 sulfate is 159.62 grams per mole. 159.62, where's it go? Bottom with G4 grams. On top, we go to 1, and we're going to get a really small number. So we take 1.59 divided by 159.62, and I want to round to 4 decimals, but when I do this, it actually rounds to 0.01. Okay, so technically we get 0.01. I put 00 to round that out, but that would be moles of our copper 2 sulfate. Now, what we are after is this X. So to find X, what we would do is this. We would take our moles of water. You always put moles of water in this scenario on top. So we're going to put 0.0505 moles H2O. And you always divide the water by the number of moles of that anhydrous compound, which is 0.01. Okay? And I'm just going to label this moles copper 2 sulfate. So then I turn to my calculator. And I'm going to talk about this before I write it down. Turn to my calculator, and we have this. 0.0505 divided by 0.01. I press enter, and in my calculator, I get 5.05. But remember, this X here can only be a whole number. So 5.05 is close enough to what whole number? Yep. And so we would say, hey, this equals 5. And so all we would have to do to write down our formula is we would say, okay, we would have Cu SO4 dot 5 H2O, and our name of this compound would be copper 2 sulfate. And what is the prefix for 5? Penta. And how do we indicate that we have a water? Yep, pentahydrate. Okay, and so that would be our answer. But the key to this is always put moles water divided by your moles of your anhydrous compound. Okay, questions? Does anybody need this? Okay. We got one more slide. It's a series of steps. I'll talk about why we have it. But last call. Anybody need it? Okay, so here we go. So our last part of not only section 5, but of chapter number 11 is this. In a lab environment, that's what I'm going to start gearing you more and more towards. If we had a hydrate, what you would do, you would take that hydrated compound, you would get the measurement, the mass right away. You put it on the scale. Then you would heat it up because you're evaporating that water. You'd let it cool, and then you take the dehydrated without water compound and you put it back on the scale. You would measure it. It should be smaller because we got rid of the water. From that value, we would have hydrated and anhydrous compound there, and we would subtract those two. We could find grams of water, which means we could find moles of water, and then we can have grams of anhydrous, which again, we can have moles of anhydrous, and we can determine the ratio of water to that formula or that compound there. Okay, we could go through that process that we just talked about and do the math to that and get to that point. So, any questions?